Hello, everyone. First of all, I would like to thank the organizers for inviting me. I was asked to provide an overview about gas dynamics across cosmic time. This is a very wide subject with a very long history. For example, here I'm showing one of the first high-quality velocity fields for an external galaxy, M101, which dates back to Rockstad and Shostak in 1971. So exactly half a century ago, we started to have emission line data cubes and use them to study a variety of topics in galaxy evolution. For example, rotation and non-circular motions, the relationship between angular momentum and galaxy morphology, the connection between disk stability and star formation, the one between gas turbulence and stellar origin feedback, and then gas removal processes, gas accretion, galaxy interactions, and so on. Another very important reason to study gas dynamics is that we can shed new light on the dark matter problem. We can derive rotation curves and infer the properties of dark matter halos. And for example, we can study the cusp versus core problem, the stellar mass halo mass relation, and other things. We can study dynamical scaling laws such as the Tully-Fisher relation and others. And we can also test alternatives to lambda CDM like modified gravity and MOND. Clearly, in 20 minutes, I won't have time to go through all these issues, so I decided to focus this talk on rotation curves and dynamical scaling laws. But first of all, I would like to start with some basic theory. So let me remind you that if we have a stationary axis-symmetric system embedded in a gravitational potential in cylindrical coordinates, the circular velocity square is by definition r times the radial derivative of the potential, and this is given by two main terms. We have the mean azimuthal velocity square, which is essentially the rotation velocity that we can infer from velocity fields. And then we have a much more complex term, which as a leading order goes like the radial component of the velocity dispersion tensor. This is not in generally measurable in external galaxies, but as an order of magnitude, it goes like the line of sight velocity dispersion, which is what we measure from the width of the emission lines. But now for cold gas disks in the nearby universe, we have an extreme simplification because in general, the rotation velocity is much larger than the line of sight velocity dispersion. And so essentially the circular velocity to a good approximation is given by the rotation velocity that we can measure. And we can also use a thin disk approximation because of this fact. So what we have to do in practice is a deprojection from the sky plane to the galaxy plane. So if you have a circular orbit, this is the relevant equation. We want to infer the rotation velocity at a given radius. And to do that, we need to know a number of geometric parameters, which are the galaxy center, the position angle, the inclination angle, and the systemic velocity. So nowadays, there are a number of codes that can do this deprojection for you. In general, I would suggest to use 3D codes that fit directly the data cube by passing the two-dimensional velocity field. And this is strongly recommended because with this approach, we can take beam smoothing effects into account and model the full shape of the line profile at each spatial position. And there are several codes that can do this in a nearly automatic fashion. The rest of this talk is divided in two parts. I will start with the nearby universe, and then I will move to the high redshift universe. With high redshift, I mean Z larger than 1. Well, let me start with Z equal to 0. In particular, we'll discuss the H-alpha line in the optical, the CO in the sub-millimeter, and the H1 line in the radial. So each one of these lines has advantages and disadvantages. The H-alpha has a long-standing history going back to Vera Rubin and collaborators. One of the key advantages has always been the spatial resolution, which is of the order of a few arcseconds or even less nowadays with adaptive optics. The H-alpha line is bright, so we can build large statistical samples. For example, if we take Khalifa, Manga, and Sami all together, we have something of the order of 8,000 galaxies with spatially resolved H-alpha data. And also this line is accessible at higher redshift moving into the near infrared. So we can have a consistent line over a broad range of the history of the universe. There are also disadvantages. First of all, we can trace only the inner star-forming disk. The non-circular motions may be important, driven by spiral arms, bars, and stellar and AGN feedback. So depending on your science goal, it could or could not be a good line to use. And occasionally, we can also have that the ratio between the rotation velocity and sigma is of the order of 1. So if you are interested in the circular velocity, then one has to take into account the pressure support. Now, the CO line has also typically good resolution thanks to the power of interferometry. Usually, we used to have resolution of the order of 4 or 5 arc seconds. Now with ALMA, we can push to 1 arc second or even less. The great advantage of this line is that CO is generally dynamically cold, so we don't need to worry about pressure support. This line is also accessible at higher redshift, in principle up to redshift 7 or so with ALMA, but we are going to look at brighter, higher CO transitions, so we don't necessarily probe the same physical state of the molecular gas. Again, one of the disadvantages is that we trace only the inner galaxy regions. Moreover, the CO line becomes inefficient in low metallicity dwarf galaxies because of the conversion factor between H2 and CO, and interferometry is time costly. So at the moment, we don't have very large samples. To make an example, the Karma Edge survey is one of the largest surveys in CO over the past years, and it has 126 galaxies, which of course is much less than the several hundreds that we have with the optical IFU surveys. Finally, the atomic gas can be probed using H1 interferometry at 21 centimeters. One of the key advantages here is that the H1 emission is generally very extended, about twice the stellar disk, so we can probe out to the outermost regions of galaxies. Moreover, the H1 is probing the bulk of the ISM because in the local universe, the H1 mass is typically larger than the H2 mass. And again, the velocity dispersion is relatively small, so we don't have to worry about pressure support unless we look at extreme dwarf galaxies with rotation velocities below 30 kilometers per second. The main disadvantage of the H1 is that it's only observable at redshift 0 at the moment. The record for H1 detection in emission in individual galaxies is around 0.4, but these observations are very difficult to do. Also, H1 interferometry is time costly, so again, we don't have large samples, and the spatial resolution is limited. As far as I know, the record is 2 arc second, actually from myself using the VLA, but most of the surveys are between 5 and 30 arc seconds, actually closer to 30 than 5. But I want to stress that these limitations are mostly technical in nature, and several of them will be overcome with SKA and its pathfinders, such as ASCAP in Australia, MIRCAT in South Africa, Apertif in the Netherlands, and the upgrade GMRT in India. So the future of H1 surveys is very promising. Now, one of the best approaches is to combine data from different tracers. This is what we did in the Spark project, in which we took H1 and H-alpha rotation curves from the literature and combined them together. And we have also supplemented galaxies with Spitzer photometry at 3.6 micron in order to probe the stellar mass distribution. So in this plot, you see 175 rotation curves in a log-log scale, color-coded by the value of the effective surface brightness at 3.6 micron, which is essentially equivalent to an effective stellar surface density. And you can see a nice rainbow here because low mass, low surface brightness galaxies tend to have slowly rising rotation curves that reach the flat part only in the outermost regions, typically beyond 10 kpc, whereas high mass, high surface brightness galaxies have steeply rising rotation curves, and several of them reach the flat part already within 1 kpc. So from this simple plot, it's already clear that there is a close link between the shapes of rotation curves and the distribution of baryons in galaxies. We can quantify this connection by looking at dynamical scaling laws. For example, here I'm showing two so-called asymptotic scaling laws in the sense that they concern quantities that are measured either for r that tends to infinity or for r that tends to 0. So on the left, you see the baryonic-Talley-Fisher relation, which is a very well-known scaling relation, but I want to clarify a few points which are often misrepresented in the literature. If we want to minimize the scatter, it's clear that we have to use the baryonic mass, which is the sum of stars and gas in the disk, on one axis, and on the other axis, V flat, which is the mean circular velocity along the flat part of the rotation curve. I want to stress that this is the circular velocity, not the rotational velocity. In fact, when we go down to low mass, extremely low mass galaxies, we need to correct the observed rotation velocities for the pressure support using the asymmetric drift correction. And if you assume an isotropic exponential disk, it's actually a relatively simple formula. Now, this relation is extremely extended. These are almost 6 orders of magnitude in baryonic mass. As you can see, it's linear, and the slope is very close to 4. The precise value of the slope may depend on your fitting technique. I suggest you to check this bias line fit code, which was written by myself together with Eric Desmond in Python. It's very easy to use if you need to fit aligned data in a Bayesian context. But actually, in this plot, I am fixing the slope to 4, and I'm only fitting for renormalization. This is interesting because if you fix the slope to 4, the normalization is equivalent to an acceleration scale simply by dimensional arguments. So if you divide the normalization by the gravitational constant, you will get a characteristic acceleration scale for galaxies of the order of 10 to the minus 10 meters per square arc second. The other relation is less well known. It's called central density relation. Now on the y-axis, we have the dynamical surface density, which can be computed from the rotation curve using a formula from Tremaine 1963. Essentially, this is driven by the inner steepness of the rotation curve. So it's complementary to the baryonic-Talley-Fisher relation because we are using a different portion of the rotation curve. And on the other axis, we have the baryonic surface density measured within one resolution element. This relation is not linear. There is a critical surface density of the order of a few hundred solar masses to parsec square. Above this value, we recover the one-to-one line. So these are regions that are baryon dominated, typically for high surface brightness galaxies. And when we go below this value, galaxies start to become dark matter dominated all the way down to the central parts. And it's also interesting to note that critical surface density by dimensional arguments is again an acceleration scale. You may simply multiply by 2 pi the gravitational constant, and you get again a value of the order of 10 to the minus 10 meters per square arc second, albeit this number plays a very different physical role with respect to the normalization of the Talley-Fisher. Now, these two relationships concern individual galaxies. So 1 point is equal to 1 galaxy. But in principle, we can use the full power from spatially resolved observations. And this is what we do in the radial acceleration relation, where now we have 2,700 points at different radii from different galaxies, which are shown as the blue color scale. The red squares are simply mean values in beams of acceleration. On the y-axis, we have the observed acceleration, which is simply the circular velocity squared divided by r, whereas on the other axis, we have the expected acceleration from the distribution of baryons that we can compute by solving the Poisson equation in cylindrical symmetry. So this very tight relationship is quantifying a local coupling between baryons and dark matter in galaxies. Essentially, if you know the distribution of baryons, you can predict the shape of the rotation curve and vice versa. And we can do this empirically with quite a good accuracy because the observed scatter in this relation is of the order of 0.12 dex. And it's actually consistent with the observational uncertainties that I'm showing down here. So in principle, the intrinsic relation may be even thinner. There is again an acceleration scale. In this case, it's very explicit. Above this acceleration scale, we have the one-to-one line. So we are in the baryon-dominated regions. Below this acceleration scale, we have the dark matter effect. But this is not a random effect. It actually follows this precise law where the observed acceleration is equal to the baryonic one times the acceleration scale, the square root of this. And remarkably, this was predicted a priori by Milgrom in 1983 using MOND. Now let me move to the high redshift universe, discussing results from near-infrared and some millimeter surveys. Over the past 10 years, there's been really an enormous progress um, thanks to HI+ surveys at redshift 1 to 3 using the HI+ and O3 lines. In my opinion, there has been two key results. One is that more than 80% of main sequence galaxies host a rotating disk. So rotation seems to be the rule up to these redshifts. And also, high redshift disks may be more turbulent than local ones, in the sense that the ratio between the rotation velocity and sigma seem to decrease with increasing redshift, at least for ionized gas. Another important question at high redshift is the shape of rotation curves. This has been debated. Some teams have found flat rotation curves, whereas other teams have found declining rotation curves. I think that this issue will be solved with JWST and ELT because we will have a much higher sensitivity to the outer regions as well as resolution. But I would like to point out that HI+ rotation curves, by their own nature, cannot extend beyond the bright star-forming disk. So we are still probing the inner baryon-dominated regions of galaxies, and at redshift 0, we can find flat, declining, or rising rotation curves in the inner parts, depending on the baryon surface density. So the outcome of this question may depend on the type of galaxy population that we are sampling. Another important question is whether the Talley-Fisher relation evolved or not with redshift. I think that it's clear that there is no strong evolution from redshift 0 to redshift 1. This has been found by many different teams using different techniques. This is one example from Ditodor and collaborators where you see the local redshift 0 stellar mass Talley-Fisher relation in green and the Talley-Fisher relation at redshift 1 in red. But the situation is unclear and strongly debated between redshift 1 and 3. In my opinion, there are a number of key issues that we need to solve if we want to address this question. For example, whether we are really measuring it flat, how do we take into account the pressure support, whether we have self-consistent stellar masses. So this redshift range is near the peak of the cosmic star formation history. So starburst and star formation may be very important, and we need to nail down the precise value of the stellar mass to light ratio. And moreover, the gas contribution can be important too, because as we know, the baryonic Talley-Fisher relation is the most fundamental one. So it's not going to be an easy job to tell whether the Talley-Fisher relation evolves with redshift or not. Finally, over the past year, there has also been a strong push towards higher redshift using the C2 line at 158 micron, which is observable with ALMA. These are just some examples of galaxies that were originally identified in different ways, observing C2. For example, these are some millimeter galaxies and quasars between redshift 4 and 5. This is a DLA around redshift 4, and this is a Lyman break galaxy almost at redshift 7. So as you can see from the C2 line, there is evidence for rotation in these systems. The current main limitation is the spatial resolution of the data. As you can see, these disks are not very well resolved, but this can be improved a lot, and we are already doing it. For example, this is a galaxy, a Starburst AGN host at redshift 4.8, which has been observed with a resolution of 700 parsec. So on the left, you see the continuum emission, which is tracing the dust distribution. In the center is the C2, which is tracing the cold gas, and on the right is the velocity field. And now we have almost 45 resolution elements across the C2 disk, which is actually comparable with H1 observations at redshift 0. So this is quite amazing. And we see clear evidence for very regular rotation, which indicates that the effects of stellar and AGN feedback on the cold ISM must be relatively weak, at least in this galaxy. You can actually showing the rotation curve for this galaxy and a mass model, which indicates that to explain these high rotation velocities, we need a central bulge component. And then the other interesting thing is that the V over sigma ratio is very high throughout the entire disk. I'm gonna skip this, but it's very interesting. It's the evolution of the velocity dispersion, which is probably needs to be revised. And then I will go to my conclusions. In the nearby universe, HI+Ha, CO, and H1 surveys have provided rotation curves for hundreds of late-type galaxies and also for some early-type galaxies. I didn't have time to discuss this, but you are welcome to ask me questions about them. We can use these rotation curves together with surface photometry to study dynamical scaling laws, which are revealing a very tight coupling between baryons and dark matter. If you think about this, this is not really natural in a lambda CDM context, but was predicted a priori by Mond. So I think that as a community, we should ask ourselves why Mond got any prediction right. If we move to the high redshift universe, it's clear, at least up to redshift 3, that rotation is extremely common. The evolution of rotation curve shapes, V over sigma ratio, and Talley-Fisher relation is debated, but for sure the JWST and the ELT will help. And finally, ALMA is revealing dynamically cold C2 disks at redshift higher than 4, possibly up to redshift 7. So I think that the combination and the synergy between these facilities is going to be really important in order to probe gas dynamics across the entire cosmic time. Thank you.